Hello and welcome to part 4 of this video series for this example problem. This example problem, I've gone through the steps previously in the first 3 videos that allow us to, or when I derived expressions that will allow us to solve this problem. And just a reminder, we're solving for the temperature of a flame in an adiabatic combustion process. So if you want to get familiar with this example problem, I would suggest watching videos 1 through 3 before this. But here first in this last video here, when we will perform this calculation in order to solve for the temperature of our flame, first we need to define a function that will allow us to return the integral of the equation 107, which we took a look at in part 3 of this video series. And just a reminder, equation 107 shows the dependence of heat capacity on temperature when we have a wide fluctuation in temperature. So like a combustion reaction, when we have gases at an ideal gas state and then heat those up to, let's say, temperatures of 1,000 kelvins or 2,000 kelvins or maybe even 3,000 kelvins. So I'm going to go ahead and define a function here. So we'll define integrate Cp for Cp being heat capacity, and this will obviously be dependent on temperature here. So we will have to supply temperature. And what we'll want to return here is our integral of equation 107. Now, if you remember equation 107, the first term in equation 107 is just a constant a. Now, we didn't take the integral of a, but we know the integral of a is just a times, t in this case. So what I'm going to do here is do p dot igc, p dot iga. And what this cp iga is, I explained this in, I think it was either part 2 or part 3 of this video series. We imported in this CHE tools, essentially it's pre-written code that gives us values that we could just plug in that are already pre-coded in, so we don't have to type in this exact number for the parameter a for the equation 107. And it's just called here the CP, so heat capacity ideal gas parameter a. So that's its name. So this will be multiplied by t. And from here, we will add, if you remember, the second term was the constant d times this expression here. And taking the integral of this expression is c times the hyperbolic cotangent of c divided by t. So actually what I'm going to do here is, instead of writing the hyperbolic cotangent, I'm actually going to divide. So I'm going to essentially put 1 over the hyperbolic tangent. But we have to remember here that we had to multiply by the parameter b here, since that was a constant, and we didn't add that in when we computed the integral of that term there. So I have p dot cp igb, and here we will multiply by p dot cp igc, and this will be divided by the hyperbolic tangent here. So we'll use our numerical Python, so np dot hyperbolic tangent, and this is c divided by t. So p dot cp igc divided by t. Okay, so it looks like our parentheses are good. Look good there. Okay, so this last term here was the constant d times this term here. So this term, and computing the integral of this term here, we got negative e times the hyperbolic tangent of e divided by t. And we had to make sure I've already done it here, but we had to make sure that we have this subtraction sign in here because we have a minus in front. So we will subtract, again, multiplying the constant d by this term, p, lowercase p dot cp igd. And this is times p dot cp ige, and then this is times let's see here, this is times the hyperbolic tangent, so np dot tan h and this will be divided by, E divided by T will be in our hyperbolic tangent here. So we'll have P dot Cp IgE divided by temperature. Okay, and it looks like we are matched up there. Looks good. Let's make sure it runs here. Okay, so what we can do here is we can go ahead, if I type in P.HFIG, and if you remember, our P variable name here is attached to this, essentially a library here. We have an array here of all the compounds that we will be working with in this example problem. So this P.HFIG will give us the enthalpy of formation of all of these compounds here. So if I press Shift Enter here, you can see we have all of the enthalpy of formations, and this Ig is ideal gas for these compounds here. So what we can do here is we can take a look and see how this changes if we take into account a big fluctuation in temperature here. So let's say we have an ideal gas state of these substances and then combust them to a state, let's say, of 1,000 kelvins. So how we can do that is, well, we will add our integral here, and our temperature will be 1,000 kelvins. So integrate Cp, and this will be 1,000 kelvins. And we'll obviously have to subtract here the integral of these components here, or these substances at the ideal gas state 298, since we want to look at the change in the heat capacity here. So integrate Cp 298. Okay, so this is the answer we get here. So we can see the change here, and you might look and say, well, this is a very, very large change. Why? Well, actually what we need to do here, because we have units here are a little bit messy. This heat of formation right here, this pre-written code, it has it in units of joules per mole. However, here what we're returning is joules per kilomole. So what we need to do here is divide this here, our expression here for integrate Cp, we need to divide this by 1,000 so that we can have similar units here, so that we're actually getting the accurate answer here. So if we run that, oh, we have a syntax error. Oh, need a divide here. So if you run this, so there we are. So here is our difference, and if I type in P.HFIG, we can see the differences here in our delta H here, essentially, if we were to have a process where we heat these up to 1,000 kelvins. So essentially what this is telling us is that if we take our reaction here, this combustion reaction, and we take it from an ideal gas state to 298 kelvins and heat it up to 1,000 kelvins, this is the enthalpy of formation that will be needed in order to carry out that process. However, what you may notice, and I said this just a minute ago, is these here are in joules per mole. So this is for 1 mole of each of our compounds here. So methane, ethane, propane, oxygen, nitrogen, and so forth. However, what we need to get at here is the number of moles of each of these compounds that we are using in this reaction. Now, if you'll remember, in part 1 of this video series, we basically laid out the stoichiometry for this combustion reaction, and we balanced out each side of the equation, if you'll remember that. Now, what we need to do here is we need to get at the number of moles of everything going into this combustion reaction and the number of moles of everything going out. So one thing that we can start off with here, and I'm going to go ahead and run all of these real quick, just because my computer did time out before. So I'm going to make sure this works. Okay. So if we start off with our fuel composition, so the number of moles of our fuel here, I'm going to set this equal to a numpy array because we're going to perform some different mathematical calculations with the array that we put this in. So if I do np.array, and what I put in here is the number of moles here of our fuel. So if we have methane, ethane, and propane, well, we have 95% methane, we have 4% ethane, and 1% propane. So entering those as decimal points, I have 0.04 and 0.01. Okay, so this right here is the number of moles of fuel that we have. So we're trying to get here at the number of moles of everything going in. Well, the fuel is only one part. We have also oxygen and nitrogen that we have to account for here. And if you look here back at part 1 of this video here that I made, so like I said, we have not only our fuel composition here, but we have our oxygen and nitrogen. We also have 3 different combustion reaction equations because we have methane, ethane, and propane. So what we need to do here is we need to get at the number of carbons and hydrogens in each of these reactions here on the left-hand side. So for our methane, ethane, and propane, so that we can get the total number of atoms of each to be able to perform the correct calculation here. So what I'm going to do here is I'm actually going to add another line of code here. And what I'm going to do is I'm going to add in another array. So I'm going to call this array, what am I going to call this array? I'm going to call it fuel CH, because this will give us basically the number of carbons and hydrogens in each of our combustion equations. So what I'm going to do is another numpy array, so array, and I actually made a typo here. It should be array. Okay, let's make sure this runs real quick. Should be good. Okay, so numpy array, and what I'm going to do here, since we essentially want to multiply the number of moles here times each of our equations because we want to get the total. So it might not make sense me explaining it to you now, so I'm just going to write it out and then I'll walk you through it, what I'm going to do here, and it'll make sense hopefully then. So for our ethane, we have 1 carbon, and I'm going to put a double bracket here. We have 1 carbon and we have 4 hydrogens, and then for ethane, we have, I put another bracket, and we have 2 carbons, and then we have 6 hydrogens. That's for ethane. And lastly, we have our propane, and we have 3 carbons and 8 hydrogens. Okay, so we close that off there. So what you'll notice here, let me get this away real quick so it's not in the way. But and it looks like we need one more bracket here. Okay, should be good there. So what you may notice here, and I'll kind of walk you through this, but if we perform a matrix multiplication here, this will get us at the total number here of moles for our fuel here. So this is what we're looking for here. So if I do something like, or we'll get at the total number of carbon and hydrogens here. So if I perform a matrix multiplication here, you'll see this is a 1/3 matrix, and this here is a 3/2 matrix. So if we multiply these two together, we will get a 1/2 matrix. So let's go ahead and do n fuel, and the matrix multiplication sign here is a @ sign. There it is, and we'll multiply this by fuel CH. And if we return this, we see again that we get a 1/2 matrix. And this makes sense here. If we add up here, essentially the number of carbons here, we get 1.06, and the number of hydrogens here, we get 4.12. So we can actually go ahead and unpack this here, because this will be useful. We'll go NC for number of carbons, and NH for the number of hydrogens. Now what you'll notice here is, like I said, we need the total number of moles of everything going in. So not only our fuel, but our oxygen and nitrogen. So how will we go about that? So this calculation here, this matrix multiplication, actually holds very, very useful here, because if we look here again at part 1 at our stoichiometric balance here, essentially what we want to do is perform a balance of our equations here in order to determine the number of moles of oxygen and the number of moles of nitrogen that go along with it in our inlet stream, obviously. So if we look here first at the number of carbon dioxide moles here, we notice that this must be equal to the number of carbons here. So that's when it becomes useful. So if we go NCO2, this will be equal to the number of carbons. And if we also look here at the number of water molecules here, so we have 2H2O, and here, over here, we have our hydrogens over here. So what we have to do is our NH2O here. So NH2O, this will be equal to the number of hydrogens divided by 2. So go the number of hydrogens divided by 2. And I'm actually going to make this a lowercase n. So, whoops. Okay. And now we can get at our moles of oxygen here. So if we look at oxygen here, we see that we have 1 oxygen here on our water, and we have 2 over here, so we'll have to divide our water by 2. So let me write out NO2. So this will equal the number of moles of water, so H2O divided by 2, and we will also add the number of moles of carbon dioxide here, and it matches up 2 and 2, so we just add the NCO2. Okay, so now we have it. Now we have the number of moles of oxygen, and all we need to do for nitrogen is just multiply by the ratio of nitrogen to oxygen. So if we go N, I guess we can go NN, N, or NN2 it should be, NN2, this will then be equal to 79 divided by 21, again the ratio, and then this will be multiplied by the number of moles of oxygen, so NO2. So this will give us now the oxygen and nitrogen that we need, and we also have here the number of moles of our fuel up here. So this is exactly what we need, since we want to be able to get the number of moles of everything going in and the number of moles of everything going out, because we know that the enthalpy of everything going in and what is going out has to be equal. So that will ultimately allow us to solve for our temperature here. So what we can do here is we can create a variable here, or just a variable name here called the number of moles in, so just NN. And what we are going to do here is we will concatenate 2 arrays here. So what this will do is just concatenate, and Python just means add together 2 arrays. So we'll need the array here of our fuel, and also the array here of the rest of what is going in here. So what we'll have here is np.concatenate. Hopefully I spelled that right. Concatenate. If I didn't spell it right, I'll have to go back, but concatenate. Yeah, that looks right. So what we'll have here is our N fuel. So N fuel first for up here in our fuel, so methane, ethane, propane. And then we will also have an array, so we'll add an array here. An array. And what we'll have here first is the number of moles of oxygen. So we'll have NO2, the number of moles of nitrogen that go along with it, so N2, and the number of moles of carbon dioxide and the number of moles of water in our inlet stream is 0, because that's produced in the combustion reaction. So let me get this out of the way. So we have a 0 and another 0 there. And I hope my syntax is okay there. NO2 is not defined. Oh, okay, I need to run this here. array. Let me take a look here. All right, so I just got a little sloppy there with my parentheses. We had to add in another bracket here for our second array for the number of moles that's not our fuel, and then close off this array here to match up these parentheses. But there wasn't any change in the thought process there. So now what we can also get at here is our n out, since we will need that as well. And here it's a little bit simpler. We're just going to have an array, so np array, array, and well, let's look here. So in a combustion reaction, our methane, ethane, and propane going out, they will be used up. So we'll have 0, 0, 0 to begin with, so 0, 0, 0. The number of moles of oxygen that will also be used up. However, the number of moles of nitrogen just goes along for the ride. So we'll have 0 for the oxygen. However, we will have N2. And we also have our products of the combustion reaction. So we have our carbon dioxide and water here. So we'll have NCO2 and NH2O. And let's make sure I didn't make any mistakes. So okay, yep, we look good here. So now that we have the number of moles of our compounds going into our stream and the number of moles of the compounds coming out of our stream, so our products, I'm going to go back up here. I'm going to take a look at this expression here. I'm going to make sure this runs here. So this we said is the number, or excuse me, this is the enthalpy needed to heat these compounds up from 298 kelvins to 1000 kelvins. So what I'm going to do here is I'm actually going to copy this just into a new line of code here. And what we can do, actually, let me do this first. I'm going to define a function, enthalpy. And what this is going to do is I'm actually just going to allow us to calculate the enthalpy here at any given temperature. So if I copy this in and change this to T, this will allow us to calculate the enthalpies here at any temperature. Okay, so let me delete this here and make sure this runs okay. Okay, and this needs to be returned. Okay, so what we need to do here is we need to multiply the enthalpy of all of our components going in. So at 298 kelvins, multiplied by the number of moles of everything going into our stream. And this must be equal to the enthalpy of everything going out. If you remember to part 1 of this video, we derived that expression multiplied by the number of moles of everything going out in our outstream. And this will allow us to solve for the temperature of our outstream because we don't know that. We know the temperature of what we're starting with, so 298 kelvins, but what we're solving for is the temperature of our products, and we know that these enthalpies have to be equal. So if we look here at the enthalpies at 298 kelvins, these are our enthalpies here. And if we look here, well, we've already taken a look here at our NN. So what we need to do here is we need to multiply, and I can go ahead and write this out. So we need to perform a dot product here in order to multiply all of these together and add them all up so that we can have one value set equal to the product, so the enthalpy of what's going out times the moles of what's going out. So in order to perform a dot product, it is np dot, and we will have the enthalpy of what's going in, so 298, and then after this we will have a comma, so we will have our NN, and if we press Shift Enter here, this will give us the value that we're looking for. So and if we also do np dot for our outstream, so we'll have H, and we had to just make a guess here, so let's just guess 2000 here, and we'll have N out, obviously, for the number of moles of everything going out. And this is the value that we get for this. Now, obviously, we need to get these two values to be equal to each other. So let's say we go to 2500. Oops. 2500. Okay, so that's way too low. Let's go to 2300. Okay, so we're getting closer. So what you can see is we need to get these two values equal so we can find this temperature here. This temperature is what we're solving for, the temperature of the flame or our outstream. So what we can do here is we can actually perform, or we can utilize the root solver function here in Python to get at this answer here. So what I'm going to do here is define a function that will essentially return to us a vector of our answers here, our temperature. So if I define just EQS for equation, and we have a vector, obviously, that we will be returned, and we will unpack that vector. So we'll be returning our temperature. So I'll set that equal to T, and we will be taking the first term in this vector. We'll only have one term, but we want to go ahead and set this here. And what we'll return is the dot product of what is going out minus the dot product of what is going in. So it's going to squeeze these together, squeeze them together until it gets to 0. That's what a root solver does. So we can solve here for this value. So if we return here, and this needs to be an array because our answer is going to be returned in an array, we will have our np dot here of what's going out. So let me copy this. Okay, and this time we will have temperature here instead of our guess. And we'll have minus what's going in. This should be a minus. So minus, let me copy and paste this. And we know that we're starting at 298 Kelvin, so we can keep that. Okay, so let's go ahead and run this and make sure it runs. Okay, so let's go ahead and utilize the root solver to get at our answer here. So if we go something like root, we'll have to supply our function here, so EQS, and then we'll also have to supply an initial guess. So let's just guess 2000 for the temperature here. Or we could guess 2300 because we got a little closer there, but it shouldn't matter. So let's go ahead and run this. Okay, so here's our answer. Our answer is it's this X here, and you'll notice, like I said, it's an array of one component, so it's a one component array. And if we want to grab our answer, if we were going to do more things with it, we could do .x and grab our answer like that. So that is the answer here. However, we were given one more thing in the problem statement that we have to take into account. We were given that this reaction is performed with 20% of excess air. So how does that change our process here? Well, one thing we'll have to do is obviously we'll have to change the number of moles of oxygen and nitrogen here because we have that excess air. So, and just real quick, the reason that we want to add excess air into a combustion reaction like this is because we want to have, you could think of it sort of as an equal reaction. We definitely don't want to have more fuel reacting than we do air, because that'll create a lot more pollutants, and you can get things such like CO, carbon monoxide, which we obviously don't want. So this is why we add in that excess air component in a reaction such as a combustion reaction like this. So I'm just going to create a variable name excess air, and we can set this equal to anything, but since we have 20%, we'll set it equal to 0.2. And what we'll need to do here is we'll need to multiply the number of moles of oxygen here by 120%. So we'll just do 1 plus excess air. Okay, since we will have 20% excess, so if you multiply that by 1, that's just the same. So you need 120%, so 1.2. So you might say, well, we also need we need this to account in the number of moles of nitrogen too, because nitrogen is in that excess air. Well, if you'll notice here, the number of moles of nitrogen, it depends on the number of moles of O2, so we should be good there. Okay. Now, one thing we also have to account for here when given this excess air here is that we no longer have zero excess air in our outstream. What we'll have here is we will have the number of moles of O2 times that excess air, because that excess air won't be used up, or at least most of it won't be used up. So we can multiply this here by 0.2, or we can multiply it by excess air. Okay, so if we press Shift Enter there, we don't really need these, but we'll go ahead and run it down. So this here is our new answer here, and you'll notice here that the flame temperature here went down, which makes sense. If we didn't have that excess air, we would have a hotter flame. But like I said, you produce a lot more pollutants, and you can get things such as carbon monoxide, which we obviously don't want. So that's it for this video series. We've gone ahead and broken down this problem, derived the expressions that we need to know that we need the enthalpies of our reactants and products equal to each other, and ultimately we had to find out the number of moles of everything going in and the number of moles of everything going out using our stoichiometric balanced equations. And then lastly here, we just did a simple root solver in order to set both of the enthalpies equal to each other, multiplied by the number of moles of everything on each side, and root solved it to get that temperature to where both of those values would be equal. So that's it for this video. Thank you for watching.